All right, so you're very much right that this gets very confusing, right? So the way that you resolve the confusion, or a way that you can resolve the confusion, is identify what are your functions, right? And then which variables go in and which variables go out, and if only to make sure that you're not confusing your variables, right? But if the variables are not confused, then to make sure to keep track of, wait a minute, which variables are functions of which other variables. So in particular here, those are our two functions, and let's look at f first. This says that for the function f, x, y, and z are input variables, and r, s, and t are output variables. Does that make sense?
Yeah.
Okay, so let's write that down here. I'm going to come down here and make a little diagram. And we've got, I already forgot. X, Y, and Z are in. R, S, and T are out. So X, Y, Z are inputs. And then R, S, and T are the outputs. Okay. This is what f does. Let's see, what color did I use for f? F was in green. Okay. Okay, that's fine. Okay. Right. So now let's look at the next function. The next function we have. Weird. So I've got this function g. So I'll use red here. Now, what is that telling me? That would appear to tell me that I'm making a color choice here. What color have I not used here? Orange. Go with orange. So U and V are the inputs there, but X, Y, and Z are the outputs. So wait a minute, X, Y, and Z are what went into the function f, right? So, okay, so U and V go in, X, Y, and Z come out. So that must mean that our picture actually looks like this. U and V are over there. And G is like that. Is that cool? Now, actually, these labels are in our way, so I'm just going to just leave it like this. So that's the sort of the roadmap of our variables. So the question has asked. To find the Jacobian matrix of F compose G. Well, I mean, G was like this, and F was like this. So F compose G means I'm looking at first doing G and then doing F. And so, in other words, I'm composing the functions in this order. Okay. All right. So now we can just come down here, because the question, we know what the question says. It says find the Jacobian matrix.
Yeah.
Okay. All right. So, well, I can write down immediately that, and I shouldn't have done those in orange. Let me do those in green. Yes. I got in my own way again. Okay, so I can write down that the Jacobian of F composed G is the Jacobian of F times the Jacobian of G. There's the chain rule, matrix form of the chain rule. Right. So all I have to do now is write down these individual Jacobians. So, all right, so let's do that. Let's do the Jacobian of F first, just because, well, it's on the left, and that's what I'm sort of writing down. I need more space than that. Okay, Jacobian of F. By the way, don't forget, we write down Jacobians one column at a time. Each column corresponds to partials to a different input variable. Okay, so the first column here, I'm going to look at F, and I'm going to take the partials with respect to the first input variable. Let me color code a little bit better. First input variable. Look at those partials with respect to the first input variable. That gives me the first column. Everybody happy? Okay. So, all right, so I have to take the partials of r, s, and t with respect to x. And, all right, well, conveniently, r, s, and t are given. R is that. S is that. And t is that. So the partials with respect to x are 2xy, z, and minus 2x. Yeah? So 2xy, z, and minus 2x. Okay. All right, so now repeat. So let me say there's a certain amount of, you got to crank out a bunch of partial derivatives. Y and then z, each of those will give you a column. So, you got to figure out what these things are. Mm-hmm. And that fills out that matrix there. Cool?
Yep. All
right. Now, next, let's see, Jacobian of G. Well, Jacobian of G has, two columns because it has two input variables, right? And for each one of those, you're going to take partials of x, y, and z. Now, again, that's just a bunch of algebra. Notice x, y, and z are known. X is that. Y is that. Z is that. Right? So again, you just have to interpret from what's given, what you need to know. And partials with respect to u and v. And that's going to give you, here's where your u partials go, and here's where your v partials go. And that gives you stat matrix.
Yeah.
And you just multiply them out.
So how am I multiplying with the x and the y and
the
left and then the u behind the
right.
Okay,
yeah. So you've got, now keep in mind, all together, in this, let's go back up to our little chart, our little diagram. The composition function is, that is, whoops, I did it backwards, f composed g. And so this composition, f composed g, that's a function of u and v. Right, so I got to rewrite everything in terms of u and v. So if at any point I see other variables in there, I've got to rewrite them in terms of u and v. So what do I do, for example, if I see an x? Well, how is x a function of u and v? And you go back up to here and note that it's given x is that function of u and v.
Okay.
That makes sense? So in other words, just plug in.
So it's going to get pretty messy then.
Well, yeah, but there's a certain amount of stuff that has to get plugged in there. Yeah, right.
Okay. How does that relate to, like when I originally did it, I just had x squared y, xz, comma, y squared minus x squared, and then I plugged in what the uv, or like...
Yeah, so what you did is, so you actually did not use the matrix form of the chain rule, right? So what you did is you actually computed f composed g as itself as a function directly, and then didn't use the chain rule at all, or at least not the multivariable chain rule. Does that make sense?
Yeah. So I would take the Jacobian matrix of f, Jacobian matrix of g, multiply them together.
Yeah. This is the matrix form of the chain rule. Yeah. So you do this, and then that's right, and then you plug in, x, y, and z as the given functions of u and v.
Okay.
Yep.
Should I get the same answer or probably not?
Oh yeah, absolutely. Well, you better get the same answer. Here's a good rule in math: if a question is well posed, and if you get two answers to it, they better be the same. Right? Otherwise, it's a bad question. Yeah.
Okay.
Yep. I mean, your answer might algebraically look different, but it should be identical. Okay. It should be equivalent. Okay, is everybody happy with number one here? Okay. So, by the way, when you multiply this out, now let's think about dimensions. When you multiply a matrix like this times a matrix like that, we're going to be looking at the different rows here. There's 3 different rows, so the matrix we're looking at is going to have 3 different rows. Right? And then we're going to be looking at the columns. There's 2 columns on the right matrix. That means that this product has 2 columns. And so altogether, when we multiply this out, the product is going to have that shape. Right, now let's talk. Does that make sense to everybody? Okay. Now let's talk about what those are. What are these? What are these numbers? Well, this, don't forget, is the Jacobian of the composition, and the composition here. The composition gives R, S, and T as functions of U and V. And that means that what we've just computed are the partials of R, S, and T with respect to U and V. The first column is the U partials, and the second column is the V partials. So what I've computed with this matrix product is partial of R with respect to U, partial of S with respect to U, partial of T with respect to U, partial of R with respect to V, partial of S with respect to V, partial of T with respect to V. So notice, again, as required, these are the partials of R, S, and T. Here, let me do this. Make a better color choice here. That's the partials of R, S, and T with respect to U and V. Okay, so the question 2 here, I guess I should have started a new recording. Oh well. The question was to compute the partial of S with respect to U.
I have a quick question. Does
Yeah.
one column here mean like
Yeah, we'll get to
S1
that.
and partial of U2?
No, we'll get to that in a moment. Yeah. So, great question, but let me finish this off first. So, partial of S with respect to U, notice, is that one. So we're just going to be interested in that particular element of this matrix. Is everybody happy with that so far? Yeah. Okay. Okay. So now to your question, what do we do with the 1 and the 2? Well, the 1 and the 2. This 1 and this 2 tells you the values of U and V at which we're interested in this matrix. Right? So you might say, so those are the values. Those are the values of these variables that we're going to plug in. And so you just take those values and plug into here. U equals 1 and V equals 2. Yeah. Does that make sense?
Yeah.
Okay. Everybody thinking about it? Okay. Okay.
So it's not the value of S?
No, because so now let's look at this function. Don't forget what the composition function is. The composition is this right here, right? And if you're interested in the derivatives of a function, derivatives are evaluated at points in the domain. Yeah. So I mean, think about in single variable calculus. If y is equal to f of x, you talk about f prime of x. And talk about f prime of y, it doesn't make any sense, right? So it's input values where functions and their derivatives are defined, and f composed g has it as its input variables u and v. So yeah. Right. Okay, is everybody happy with these 2 questions? Okay, go ahead and stop it.